Alright, in this video we're going to look at the derivation of several different forms of the differential equations that we can have for either voltage or current, whether we're looking at series elements or even looking at parallel systems. So generally there's going to be three types of forms that we're going to be looking at, whether it's series or parallel, and we're going to call those basically, and this is just for lack of better phrases, but just to differentiate the different types. We're going to call them the integral form, the derivative form, and we're going to call one of the methods the substitution method in order to actually gain the differential equation into the specific form that we're actually looking at. Now, generally, we're going to either be concerning ourselves with the inductor current or the voltage across the capacitor and looking for the total response for that differential equation solution. But sorry, there's a bug that's right in here while I'm videoing. Must be psyched on differential equation stuff too. But generally, I wanted to go ahead and put up these derivations as a way to streamline these methods so you guys can see just the individual derivations themselves, so that once we actually start getting into solving these problems, you're already going to be familiar with this method, and so it's going to make working through these problems way easier. So let's first start looking at series elements. Now, with series elements, we're really mainly concerned with the idea of KVL, where basically all the voltages for each element are going to be different, but their currents are actually going to be the same. And those two concepts right there actually allow us to do a lot of manipulation with the equations themselves. So let's take a look here. Now, obviously, with series elements here, we're going to have R, L, and C, so our resistor, our inductor, and our capacitor. So the voltage across the resistor is different from the inductor as well as the capacitor. Current's always going to be the same. So whatever current's flowing through the resistor is the same for the inductor, same for the capacitor, which I think is just kind of just awesome and cool, because we're talking about a dynamic system. We're talking about exponential rise or decay with maybe some oscillation that's thrown there if the system has too little resistance. So by KVL, VL of t plus VR of t plus VC of t is equal to Vs, so the source voltage. So just as a reminder, if we're concerning ourselves with series elements, IL of t, IC of t, IR of t, and is basically all going to be the same. So there's no reason to always just write L, C, and R. We can also just rewrite the inductor current as just being I of t. So the first two equations that we're going to concern ourselves with are basically a direct application from KVL, in which we just simply expand the KVL equation by the current voltage characteristics. And when we do that, we immediately have the entire equation in the form of the inductor's current. Okay? So if we take basically that KVL equation right here, VL of t plus VR of t plus VC of t, and we expand that by the individual current voltage characteristics, in this case, L dit dt, R I of t, and then 1 over c times the integral of 0 to t of I tau d tau plus its initial condition, then the entire equation is already in the form of I of t. One equation, one unknown. In this case, the unknown would be the inductor current. And so right here, we've already expanded it into an equation that we can start working with, but we're not ready to solve it just yet. So we need to actually go ahead and isolate that highest order derivative to put the equation into its standard form. And once we do that, we could actually start solving the differential equation right there. So to put it in standard form, we divide through the entire equation, both sides, by L. So then we get di of t dt plus R over L times I of t plus 1 over LC times the integral of 0 to t of I tau d tau. But then at the end, VC of 0 plus is divided by L, and also Vs is divided by L. Don't forget that you have to divide through completely in order to get this form of Vs over L. And this form right here, we could actually start solving, and I call that the integral form. Now, if we actually wanted, because this is a second order system, we usually see a second order derivative. We can easily also go ahead and put the integral form into its derivative form simply by taking its derivative. Now, we take its derivative, first order differential becomes a second order derivative, r over L times dit dt plus 1 over c times it, and then here, these two, well, in this term, this would be the initial condition, and that would be the voltage source divided by L. These constants would actually just, the derivative of constant 0, so both of these would go to 0. But the thing is that both of these forms, the integral form and the derivative form, if we took the Laplace transformation of both of these and solved for I of s, and then actually took I of s once we did partial fraction expansion, and we took that back into the time domain, we would get the same exact solution for I of t, which is kind of cool, and this is something that we're actually going to be proving throughout example problems. Now, that's for the inductor current. What can we do, though, if we have to find the voltage across the capacitor? Here's the problem. Right here, we got VL of t plus VR of t plus VC of t is equal to Vs. That's one equation, 3 unknowns. And if we have 3 unknowns, we may have to manipulate the equation a little bit in order to actually get everything in terms of VC of t. See, right here, our variable for VC of t we already have. This is what we want. So now we have to go through and manipulate that equation, that KVL equation, into a form in which we could actually get the entire equation into basically VC of t. But how could we do that? How could we get the entire equation in terms of VC of t? Well, let's think about this. What do the elements have in common? That's current. So the current through the resistor is the same as the current through the inductor, same as the current through the capacitor. What could possibly put everything in terms of VC of t? Well, let's move over to the next board. Maybe we'll see. All right. All right. So sure enough, IL of t is equal to IR of t is equal to IC of t because of the series relationship. What's that also equal to? C dVct dt. Because of that current relationship, they all equal to basically a form that includes the variable that we're looking for, Vc of t, and that includes the derivative. So in this case, VL of t plus VR of t plus Vc of t is equal to Vs. Well, we can go ahead and expand the first two variables here, VL of t and VR of t, by its current voltage characteristics. So we get L dit dt plus R times IT. We leave alone VC of t because that's what we already want. We want the equation to be in terms of this variable of VC of t, so we leave that alone. And that's equal to Vs. But what we can do now is take C dVct dt, substitute that in where we have RIT, and then also substitute that in where we have L dit dt. We substitute that in, and then all of a sudden, if we look right here at these two substitutions, we're going to get the equation all in terms of Vc of t. So one equation, one unknown. But look what happens when we substitute those in. We're substituting derivatives in which we may actually have to take the derivative of the derivative. So that gives us a second order derivative. So down here, sure enough, we have actually gained an entire equation, a second order differential equation in terms of Vc of t. LCD squared, Vc of t, dt squared, plus RC, dVc of t dt, plus Vc of t is equal to Vs. All we have to do is just isolate the highest order derivative, put it into standard form, and sure enough, we derive a second order differential equation all in terms of Vc of t. So d squared Vc of t dt squared plus r over L dVct dt plus 1 over LC Vc of t is equal to Vs over LC. And this is what I like to say is the substitution method in order to manipulate the KVL equation all in terms of Vc of t. So in summary, for basically series elements, the integral method, the integral form and the derivative form are for the inductor's current. That's just basically an expansion of the KVL equation directly into the variable of I of t, which is also the inductor's current, or we can manipulate the entire equation through substitution in order to get the second order derivative form for